Hello, this is not Stephen Hawking, that came back to life. Today I would like to explore with you the Big Bang Theory. The cornerstone of physics, astrophysics, theoretical physicist, and even quantum physics. On July 18, 2022, the James Webb Space Telescope project released its first full-color images. So let's talk about what it is or it is not. But the fact is that this red blob shouldn't be there based on our current understandings. But there it is, a distant galaxy in the background of James Webb's deep field.
The age of the universe is one of the most fundamental questions in cosmology. It tells us how long the universe has been expanding since the Big Bang, the colossal explosion that created everything we see today. For decades, scientists have been using two main methods to estimate the age of the universe. The first one is based on measuring the rate of expansion of the universe, known as the Hubble constant. By observing how fast galaxies are moving away from us, we can calculate how long it took them to reach their current positions, and thus how long ago the Big Bang happened. The second method is based on studying the oldest stars in the universe, which are found in ancient globular clusters. By measuring their brightness and color, we can estimate their age and infer the minimum age of the universe. Using these methods, scientists have agreed on a value of about 13.8 billion years for the age of the universe, with an uncertainty of about 20 million years. This value is consistent with various observations and models of cosmic microwave background radiation, which is the leftover heat from the Big Bang that fills the entire sky.
Now let's hear what Neil deGrasse Tyson have to say about this new findings.
In the early universe, go back to the Big Bang and you have this cauldron of matter and energy. Well, we don't have stars yet. We don't have galaxies yet, this organizing principle of stars as they gather into cities. No, it's just matter and energy. And it takes a while for the expanding universe to cool so that matter can coalesce to make stars and ultimately galaxies. So there's a period of time after light was sent free in the universe, because before then it was constantly interacting with matter and the universe was just a fog. Light gets set free once we've expanded enough. This happened around 400,000 years after the Big Bang. Now light is set free, but okay, we don't have any objects that generate light. Okay, so in this period between 400,000 years and the first stars, we call that the Dark Ages. There was nothing there to radiate. Yes, there was leftover light from the Big Bang, but no objects talking to us. So we calculate, we put out our best understanding of the universe for gravity, quantum physics, nuclear fusion physics, and all of this. We put on our best thinking caps and say, it'll take about this long, 1 or 2 billion years, just to get the stars going. And then you need enough stars in a place to gather and make a galaxy. And a galaxy will have enough light for you to see from a great distance. It'd be very hard to see individual stars. Okay, that's our model of the early universe. Now we say, we don't understand how galaxies are born. Let's make a telescope to help us. So we spec the next generation space telescope after Hubble to be exquisitely tuned to show us galaxies being born. And we expect it to show us galaxies at the end of the Dark Ages, at the birth of objects in the universe. So we design and build this telescope, the James Webb Space Telescope. Now, what's different about it? Because we'd expect galaxies that are just born to be giving off intense amounts of high energy light, ultraviolet light especially, because certain classes of brand new stars give off copious amounts of this kind of light. How do we see those galaxies today? Well, if that was that long ago and the universe has expanded, that ultraviolet light is no longer ultraviolet light. No, over the expansion of the universe, those wavelengths have been stretched 13.8 billion years later. Today, ultraviolet light emitted at the early universe has been stretched to become infrared light. Oh my gosh, okay? Well, we knew this would happen, but it's amazing that we can fool the universe into saying, we know you gave off ultraviolet when you're born, and we're gonna look for you in the infrared. You're not gonna get by us. So we make the James Webb Space Telescope exquisitely tuned to see infrared emission that started out as ultraviolet in the early universe. Bada bing, we turn on the telescope. Oh, by the way, infrared is also good for looking inside gas clouds that are sitting in front of our nose to see the birth of stars, otherwise cloaked in the gas clouds from which they're born. Cloaked, you can't see it with visible light because the visible light scatters and you can't see it. It's hidden if you're using visible light. But if you use infrared light, that infrared comes from the stars and pops right out of those gas clouds. And you see where all the stars are, as well as the newborn planets in orbit around them. So the James Webb Space Telescope is good for stuff nearby, just as it's good for stuff long ago. All right, so now let's tune the telescope in to galaxies being born. And oh my gosh, who ordered this? We're finding galaxies in the dark ages. We had no idea. No idea. And I'm told the lead researcher was so shocked by this, he spit out his coffee when he realized what kind of data he had on his hands. So I can give a list. What's the list? Either we don't understand how galaxies are formed. Of course, we don't fully understand it. That's why we built the telescope. But all our understanding about matter and energy that tells us that there should be a dark ages, something had to change. We got to go back and adjust that somehow in ways we don't know or understand yet. Or some new kind of object, unlike any other objects we've ever seen, had no trouble forming in the dark ages. Or us placing it in the dark ages is somehow flawed. We're basing this on just pictures of these galaxies and what their properties are via pictures. What we are waiting for now is we want to get a spectrum of those galaxies, of those objects. Let me not even call them galaxies, because they could be something else. You can tell us what chemical elements are there. A rainbow is a spectrum of the sun, right? White light comes through, goes through a raindrop, out comes its component colors. If you look even more carefully at it, those colors reveal the chemistry of what's going on in the sun, the chemical elements that are there. You can also find out other things, like how fast is the sun rotating. All kinds of things you can find out when you get the spectrum. So, if we get the spectrum of these objects, we'll know what they're made of. We will even be able to better place them in distance. Maybe there's something contaminating our estimate of its distance, and maybe they're really on the edge of the dark ages, but somehow they're masquerading as though they're a little farther away, deep within the dark age. Who knows?
Now let's hear what Michio Kakuo have to say about this new findings.
And a lot more developed than we thought. And why does that matter? Well, for one thing, it could pretty much rewrite a whole bunch of astrophysics textbooks. So, of course, we called up the legendary theoretical physicist Michio Kaku. He's the futurist who always has me dreaming of the cosmos and the author of a bunch of books that might need to be tweaked now if it turns out that the universe is older than we think. Hey, Professor, I'm thinking of some of my favorites. The God equation, physics of the future, future of humanity. Most of them say the universe is about 13 billion years old. What if it's not?
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. Now, it takes many billions of years to create a galaxy, like the Milky Way galaxy, with 100 billion stars, many billions of years old. But the James Webb Telescope has identified 6 galaxies that exist half a billion years after the Big Bang that are up to 10 times bigger than the Milky Way galaxy. That shouldn't happen. There should not be primordial galaxies that are bigger than the Milky Way galaxy that are only 500 million years old. Something is wrong. We may have to revise our theory of the creation of the universe.
And so we're possibly looking at a universe that's much older than we think it is, and we're also possibly looking at maybe this is an optical illusion. Are those the two options here?
That's right. Some people say it's an optical illusion. You see, according to Einstein, gravity can act like glass. The glass, of course, you can make a magnifying glass. With gravity, you too can bend space and time to create a a magnifying lens. So you think that these galaxies are huge when they're actually baby galaxies. Now, I personally think that the solution to the problem is these are not baby galaxies at all. They're actually monstrous black holes. Black holes that formed after the instant of creation. That's baffling scientists because they don't fit in the normal sequence of the birth of a galaxy. So I personally think that we're actually looking at monster black holes where perhaps new laws of physics are emerging. And again, if you can figure all this out, there could be a Nobel Prize waiting for you.
I'm sorry, you're saying that these galaxies, these 6 galaxies that look kind of like galaxies are actually black holes?
Yeah, that's one theory, because we think that at the center of our own Milky Way galaxy, there is a raging black hole that is 2 to 3 million times more massive than our sun. In fact, we now believe that at the center of almost every galaxy in the universe, there's a monstrous black hole that could be millions to billions of times more massive than our own sun.
So it looks like the more we look into the skies, even more mysteries appear. This findings changes the whole picture of the expansion of the early universe, since we thought we had everything calculated after the Planck's epoch, because before that only quantum physics can predict with certain uncertainty. So to conclude, now we know that we don't know, either before or after Planck's epoch. Thanks for watching, and as a human never stop asking questions. Till next time.